For the RCU, the read copy update mechanism in Linux, this RCU mechanism is considered as an advanced lightweight synchronization mechanism, which was integrated into Linux kernel in 2002. The RCU mechanism is used widely in Linux kernel. For example, it has been widely used in networking subsystems, the memory subsystem, the virtual file system, and more. RCU is also used by different operating systems, like the BSD as an example. Also, there is a user space RCU library. This library is called library URCU. As opposed to common Linux synchronization mechanisms, RCU readers are not locked. The shared resource that the RCU mechanism protects must be accessed via a pointer. The RCU core API is quite small and consists of only six methods: the RCU read lock, the RCU read unlock, the call RCU, the synchronize RCU, the RCU assign pointer, the RCU dereference. All of these are the different APIs that are used to allow the synchronization using the read copy update mechanism. Also, I want you to keep in mind that there are about 20 RCU application programming interfaces with different API structures and implementations. And the RCU mechanism provide access for multiple reader and writer to a shared resource. That means when a writer wants to update that resource, it creates a copy of the resource and then update the resource and assign the pointer to a point in the new copy of the resource. And afterwards, the old version of that resource is freed when it's no longer needed. So updating a pointer would be considered as an atomic operation. And that means the reader can access that resource before or even after the update is completed, but not during the update operation itself. In terms of performance, the RCU synchronization mechanism is best suited to many scenarios where reads are frequent and writes are rare. So as we understood so far, different synchronization mechanisms or concurrently mechanisms in Linux and Unix. Now I want you to also be familiar of how these concurrency mechanisms can be seen in Solaris. In addition to the concurrency mechanisms of Unix, also Solaris supports 4 thread synchronization primitives. The first one is called mutual exclusion on mutex locks and semaphores, multiple reader, single writer locks, and also condition variables. Solaris implements these primitives within the kernel for kernel threads. They are also provided in the threads library for user level threads. As you can see in this figure, the data structure for these primitives are illustrated. The first one is the mutex lock, the second one is the semaphore, the third one reader and writer, and the third one is the condition variable. The initialization function for the primitives fill in some of the data members. And once a synchronization object is created, there are essentially only 2 operations that can be performed: enter and release, or lock and unlock. There are no mechanisms in the kernel or even in the threads library to enforce mutual exclusion or even to prevent a deadlock, such that if a thread attempts to access a piece of data or code, which is supposed to be protected, but doesn't use the appropriate synchronization primitive, then such access would even occur. If a thread locks an object and then fails to unlock it, no kernel action is taken. Just keep in mind that all of the synchronization primitives would require the existence of hardware instruction that allows an object to be tested and set in one atomic operation. If we will now address the first synchronization primitives in Solaris, which is the mutex. A mutex is generally used to ensure that only one thread at a time can access the resource protected by the mutex. And the thread that locks the mutex must be the one that actually unlocks it. A thread attempts to acquire mutex lock by executing the mutex enter primitive. If mutex enter cannot set the lock, which might be because it's already set by another thread, the blocking action depends on type-specific information stored in the mutex object. The default blocking policy is spin lock. A blocked thread would actually post the status of the lock while executing in a busy wait loop. And finally, an interrupt-based blocking mechanism is optional. Means the mutex would include a turn ID or like a turn variable that identify a queue of threads sleeping on this lock. So you could allow this using interrupt or without interrupt. Also, Solaris provides a classical counting semaphores with the following primitives. The first one is the sema P, the second one sema V, and then sema tri P. So for the sema P, it decrements the semaphore, so more or less like look like the decrement function we addressed before, and potentially would block the thread. The second one, which is the sema V, this is the increment function or primitive that we addressed before. It would increment the semaphore and potentially unlocking a waiting thread. The third one would be decrementing the semaphore if blocking is not required. So this one is slightly new. Again, the sema tri B primitive actually permits busy waiting. So this is one of the drawbacks of semaphore primitive usage in Solaris. The reader and writer lock allows multiple threads to have simultaneous read-only access to an object protected by the lock. And it also allows a single thread to access the object for writing at one time, while at the same time executing all readers. That means when a lock is acquired for writing, it takes on the status of write lock. And if one or more readers have acquired the lock, then that status would be read lock. Finally, condition variables are also used as initiation to different synchronization primitives in Solaris, such that they allow a waiting procedure until a particular condition is satisfied or is true. That means the condition variables are used to wait until a particular condition is satisfied. Condition variables must be used in conjunction with the mutex lock. This is the first combination that we see for the mutex lock, as well as the condition variables in Solaris. And as a matter of fact, if you check the textbook, you will see that combining the condition variables as well as the mutex, the different condition variables, and then mutex semaphores, it could be actually built in a data structure defined into a monitor that will make it a little bit more complicated as compared to traditional operating systems, but it works perfectly to allow synchronization and concurrency. Before the last operating system, I would like to cover Windows and its fundamentals, learning aspects of addressing concurrency and solutions to concurrency matrix exclusion enforcement, for example. Keep in mind that Windows provides synchronization among threads as part of the object architecture. And the most important methods of synchronization within the Windows operating system are executive dispatcher objects, user mode critical sections, slim reader writer blocks, condition variables are used as well, and finally, lock-free operations. Dispatcher objects would actually, so this is more related to the dispatcher objects, make use of wait functions. And if we would like to understand the relationship between the dispatcher objects and the wait functions, I would like to classify wait functions into three main characteristics. So wait functions allow a thread to block its own execution. The wait function do not return until the specified criteria have been met. And the type of the wait function determines the set of the criteria used. When a wait function is called, it first checks whether the wait criteria have been met. If the criteria have not been met, the calling thread would enter the wait state. It uses no processor time while waiting for the criteria to be met. The most straightforward type of wait operation or wait function is the one that waits on a single object. So we might have some scenarios where the timeout interval elapses between different functions, and handling those wait function would need some efforts from the Windows operating system to provide better synchronization. The mechanism by which the Windows operating system executive to implement synchronization facility is the family of dispatcher objects, which actually can be summarized in the following table. So we do have notification event, synchronization event, mutex, semaphore, and the waitable timer, files, processes, and threads. All of these are the dispatcher objects. The first 5 object type in this table are actually specifically designed to support synchronization, as we can see here. The remaining object types have other uses, but they also may be used for synchronization. Each dispatcher object instance can be either a signal or unsignal state. A thread can be blocked on an object in an unsignal state. The thread is released when the object enters the signal state. The mechanism in a fashion is very straightforward. How it works is a thread issue a wait request to the Windows operating system through the Windows executive layer, and then using the handler of the synchronization object, this operation is performed, such that when an object enters the signaled state, the Windows executive would release one or all of the thread objects that are waiting on that dispatcher object. So how critical section is handled in Windows? Critical sections provide a synchronization mechanism similar to what was provided by mutex objects, except that critical sections can be used only by the threads of a single process. And mutex and semaphore objects can also be used in a single process application, but critical section, on the other hand, provide a much faster and more efficient mechanism for mutual exclusion synchronization. If the system actually is a multiprocessor system, the code would attempt to acquire a spin lock at this point. And if the spin lock cannot be acquired, a dispatcher object would be used to block the thread, such that the kernel at this point would dispatch another thread to the processor. One of the common locks that we see a lot in Windows operating system is the slim read writer locks. Windows Vista in particular added a user mode reader writer, which is very similar to critical sections, where the reader-writer lock would enter the kernel to block only after attempting to use a spin lock. It is the SLIM in the sense that it is normally only requires allocation of a single pointer size piece of a memory. So the reader-writer lock enter the kernel to block only after attempting to use a spin lock. And there are two awake methods in Windows that are commonly used. The first one is called wake condition variable, and the second one called wake all condition variables. If you check the textbook, you will see the pseudocode of each of those functions. You are not required to know the pseudocode for these functions. I just want you to know that there is a SLIM reader-writer lock in the fashion that it allows synchronization, another way of allowing synchronization in Windows operating system. In addition to all of the synchronization mechanisms like the wait functions, critical sections, and the SLIM reader-writer in Windows, we also have condition variables. So the process must declare a condition variable and initiate it in some thread by calling an initialization method. Those condition variables can be used with either critical sections or within some other locks. You will see that there are different methods that will access those condition variables to sleep on some of the condition variables or to sleep all of the condition variables based on certain conditions and specific locks. There are two awake methods also would be seen in the textbook. One of them is to wake some of the condition variables or to wake all of the condition variables. Again, I don't want you to memorize these, but I just want you to know that those condition variables are used in the following scenario. You will first acquire executive lock, and then you will loop or keep checking on the value of those condition variables, and you will sleep on the condition variable if the condition variable is not satisfied. And once the condition variable is satisfied, you will perform the protected operation and then finally release the lock. So in addition to the critical section, SLIM, write and read, and even the wait of functionality, we do have lock-free synchronization in Windows operating system. Windows also relies heavily on interlocked operation for synchronization. That means the interlocked operations, they use hardware facilities to guarantee that memory locations can be read, modified, and written in a single atomic operation. For example, would include some functions as enter into a lock increment function or a compare and exchange function. Many of the synchronization primitives, they will use the interlock operation within their implementation, but these operations are also available for programmers for different situations. After we address Windows, finally, I would like to give you an overview of how Android provides concurrency and synchronization by allowing different mechanisms, including inter-process communication. As we have seen before, the Linux kernel includes a number of features that can be used for inter-process communication. Sometimes we use inter-process communication, IPC, to reflect the inter-process communication. And in Linux, we were able to see pipes, shared memory, messages, sockets even, semaphores, and signals. Android doesn't use these features for the inter-process communication, but rather adds to the kernel a new capability known as the binder. What is a binder? A binder would provide a lightweight remote procedure call, the RPC capability, that is efficient in two aspects. The first one, memory, and the second one is processing requirement. And actually, it is well suited to the requirements of embedded systems. It also used to mediate all the interactions between two processes. This is done clearly using the binder, such that a component in one process, which sometimes we call it the client process, would issue a call, and this call is directed to the binder in the kernel, which passes the call on to the destination component in the destination process, which we call it the surface. The return from the destination would go through the binder and is delivered to the calling component in the calling process. Traditionally, the term RBC would refer to either a call or a return interaction between a client process on one machine and a server process on other machine. In the Android case, the RBC mechanism works between two processes on the same system, but running on different virtual machine. The method used for communication with the binder is called IOCTL system call. The system call is a general purpose system call for device-specific input-output operation. It can be used to access device drivers and also what are called pseudocode drivers for the devices, of which binders is considered as an example. As you can see in the following figure, it illustrates the typical use of binders. The dashed vertical lines represent threads in a process. And before a process actually can make use of a surface, that surface must be known. A process that hosts the surface will spawn multiple threads so that it can handle multiple requests concurrently. Each thread makes itself known to the binder by unlocking a system call, which is the IoT CTL system call. So in this part of this week lecture, we talked about the dynamic philosopher problem and how it has been handled by two solutions of semaphore actions. The first one has caused deadlock and starvation, and the second one has freed the problems, which means it has provided solution to the synchronization and at the same time it's deadlock free. And also we have seen solution using monitors. We came across different case studies or like real examples of operating system that actually supports concurrency, including Unix, Linux, Solaris, Windows, and Android. Now let's start the second part.